Hi, my name is Lindsay Johnson. I'm a biological anthropology major, and the course I did my capstone for was Anth 370 Primate Behavior and Ecology. My presentation is on the early Eocene folivorous horse Heracitherium, specifically its thermal adaptations relevant to climate change. In the fall of 2016, Courtney Patton presented her capstone research documenting an inverse relationship between body mass and paleotemperature in the extinct primate Canius of the earliest Eocene, 56 to 52 megaanna in the Bighorn Basin, Wyoming. In her chart, the 0-meter level 56 megaanna of the Willwood Formation follows the PETM, in which rapid global warming was followed by temperature decline and increase. Meter levels 0 to 300 occur with temperature decline, and meter levels 350 to 650 are marked by increasing temperatures. Over this 3 million year period of time, the Canius primate experienced an increase, then a decrease in total body mass. To give some explanation on the graph, the bottom x-axis is the surface area of the tooth in millimeters squared, giving inference to body size. The y-axis indicates meter level, which is representative of periods of time. And the top x-axis represents temperature, which the paleotemperature curve further explains. The paleotemperature curve, which is highlighted on the graph, indicates change in temperature over time. You may notice the areas on the graph indicating biohorizon A and biohorizon B. These biohorizons indicate periods of time in which there was major faunal turnover. These give indications of mass immigration, emigration, speciation, and/or extinction. Introduction to my research. According to Bergmann's adaptive rule, there is an inverse relationship between mammalian total body mass and thermal temperature. So as it gets warm, body mass gets small, and as it gets cold, body mass gets large. In addition to numerous fossils of Canius, the Willwood Formation yields even more numbers of fossilized dental elements of the earliest known horse. Often the horse is recovered in the same localities as the primate Canius. In this study, I obtained dental-based body mass estimates following the same methods as Courtney Patton to see if Bergmann's adaptive rule is applicable to a non-primate mammal Heracitherium with the same temporal and spatial distribution. Going into this project, I had two hypotheses. Hypothesis 1, there is an inverse relationship between Heracitherium body size and paleotemperature. The null hypothesis, there is no relationship. Hypothesis 2, Heracitherium and Canius show similar patterns in thermal-related total body mass responses. The null hypothesis, there is no relationship. For my study sample, I obtained Heracitherium specimens from the 2013 to 2016 CSU Paleontology field seasons housed in the Paleontology Field School Lab. The interdisciplinary interests involved in this study include biological anthropology, primatology, primate paleontology, vertebrate paleontology, as well as paleoclimatology and conservation and ecology. Methods. I obtained linear dental metrics, the length and width, on the occlusal surface of the first mandibular molar using a Dynalite digital microscope. The data were then used to calculate surface area, and subsequently the natural logarithm of the surface area was entered into an equation for parasidactyl total body mass estimation developed by Sergei Legendre. Legendre's equation is as follows. ln of x equals a ln of y plus ln of b, where x is the total body mass in grams, y is the surface area of the tooth in millimeters squared, a is the slope, and ln of b is the intercept. Legendre has set a's and ln of b's for different systematic groupings. Specifically for parasidactyls, a equals 1.564 and ln of b equals 3.267. A difference between this equation and the equation that Courtney Patton used was hers was developed strictly for primates, and it allowed her to use the first and second mandibular molars, whereas this equation is only used for first mandibular molars. The results were then plotted against stratigraphic levels and compared to previously reported results for the primate Canius. Results 1. Surprisingly, Heracitherium body mass did not show an inverse relationship between total body mass and thermal temperature. This supports the initial null hypothesis, which states that there is no correspondence between Heracitherium total body mass and paleotemperature change. Remember, however, that this sample is limited to meter levels in which Canius was also recovered. Here are the two graphs compared against each other. On the left is the initial results of Herecotherium at Canius levels, and on the right is the graphed Canius results from the pilot study. The blue box on the Canius graph indicates 350 meters of data. This is because this particular Herecotherium sample was limited to that same 350 meters. Results 2. The interspecies comparison of Herecotherium to Canius supports the second null hypothesis, which states that there is no similarity in Herecotherium and Canius thermal-related total body mass responses. As you can see, Canius appears to exhibit Bergmann's adaptive role. However, unfortunately, Herecotherium does not present the same pattern, perhaps due to the locality restriction on this specific study, as only 16 specimens of Herecotherium were able to be utilized. Interpretation. Unlike Canius, which appears to be one species, our horse appears to represent two species. At biohorizon A, an established period of faunal turnover, the lower-level species disappears and the upper-level species shows up. However, due to small sample size, I was not confident that this could properly be assumed. So I decided to perform a new test. I decided to expand the Herecotherium sample to include meter levels without Canius. Surprisingly, the inverse relationship to temperature remained unsupported. With the added localities with known meter levels, I was able to total 35 specimens for the final result. Interpretation. Since the results from this study are not consistent with those of the Canius study, we must reject the null hypotheses regarding 1. Correlation between total body mass and paleotemperature in Herecotherium, and 2. Similar responses in the horse-primate comparison. I suggest that, at a minimum, the horse represents two species. Why? Total body mass range. The largest horse yielded a total body mass estimation of 32.7 kilograms. That's about the size of a Labrador. Whereas the smallest horse yielded a total body mass estimation of 5.6 kilograms. That's about the size of a house cat. The smallest horse was recovered below biohorizon A. The large-sized morph appears to show up in biohorizon A, with the largest horse just above at about 225 meters. Interpretation. The largest individual is nearly 6 times greater in total body mass than the smallest individual. Among extant mammals, total body mass sexual dimorphism, differences between adult males and adult females of the same species, does not exceed 2.0. Among non-domesticated modern parasodactyls like zebras and rhinos, the greatest degree of body mass dimorphism is about 2.0. Using 2.0 as a bracket for degree of sexual dimorphism, I re-examined my Herecotherium sample. The results indicate that there may be 3 extremely sexually dimorphic species, and none demonstrate an inverse relationship between total body mass and thermal temperature. Species A, our smallest species, appears on the left. With the 2.0 sexual dimorphic bracket, species A has a total body mass range estimation of 5.6 to 9.8 kilograms. Species B is our mid-sized species, highlighted in green. Its total body mass range estimation is 10.2 to 20.6 kilograms. Finally, we have species C, highlighted in yellow. Since we only have 2 specimens of species C so far, it is difficult to make inference on its size range or total body mass pattern with paleotemperature. There is a possibility that perhaps this species moved out as paleotemperature began to increase again, giving some explanation as to why we have such a small sample of them. However, the estimation of the 2 specimens' total body mass range are respectively 26.1 kilograms and 32.7 kilograms. Setting the species number aside, let's return to the primate parasodactyl comparison. Adaptive variation could contribute to differences in range distribution in this comparison. Whereas the Canius primate was an arboreal quadruped, the Herecotherium horse was a terrestrial quadruped. If times are tough, Herecotherium could easily modify its range. With larger sample sizes, if the results reported here are replicated, it would suggest disparity in susceptibility to climate change in the 2 mammalian groups. Why might there be such a stark difference between the total body masses of the 3 species? Thermal inertia. Thermal inertia is the body's ability to conduct and store heat. Larger animals are at an advantage because of their low surface area to volume ratio. The larger the size, the higher the thermal inertia. This allows for these mammals to store heat during the day and dump the heat at night. Conclusion. So which rule is right? Bergmann's rule, which favors small body mass in warm temperatures, or thermal inertia, which favors large body mass regardless of temperature? Why not both? With such a stark difference in body size that we see in this study between the 3 species of Heracitherium, clearly all of them have seemed to work out their own ways of surviving the heat. We could extend the results of this study to modern primates. Terrestrialism appeared to provide a significant behavioral response to Heracitherium that was unavailable to the arboreal Canius. This has implications for extinction risks among tropical arboreal primates today, who must face the same issue of thermal stressor in a time of human-caused deforestation. If Canius couldn't find a way to fix the problem of arboreality, how can we expect modern arboreal primates to do any differently? Here are some very possible ideas for furthering this study. We can expand dental body mass estimation data to other mammals found in association with Canius. We can also investigate folivory relative to body mass increase and thermal inertia. Additionally, we can perform stable isotope analysis to determine degree of plant consumption relative to thermal temperature. And finally, and most importantly, we need more horse specimens, especially at higher stratigraphic levels, in order to solidify what was done here in this study. Together, these studies can help reconstruct the paleo environment in which primate Canius thrived. Thank you.